This is our final lecture. In this lecture, we look at how skinning is performed in the vertex shader. We have in variables coming from the program that specify the bone IDs. These are integer IDs of the 4 bones affecting each vertex, and they are sequentially ordered. We have another in vector that specify the bone weights, the weights by which each of these 4 bones is going to be affected. And we initialize a constant that specifies the total number of bones that we have. If we have a more complex object, we'll have a larger number of bones. This is different from the 4 bones that we want to affect with every weight. Now, using this constant value, we initialize a bone transformation array. And then we sequentially fill in this array where we multiply a given set of bone IDs by their respective weights. And then we add the second transformation, which is the bone IDs of the second bone and their respective weights multiplied together. This is the vertex position that is being multiplied with the bone transform to give us the final position of the bones. The final position of the vertices after performing the bone transform. And we transform their normal vectors in exactly the same way to give us the bone transform normals. Blender provides bone weights for all bones for each vertex. That is, every vertex is affected by every bone, although very minimally by some bones. However, we would like to keep only the 4 largest weights that affect every vertex. So this is a code from your header file, United Read, which performs insertion sort to keep the 4 largest values. So it's a double loop here that loops over the number of bones and the number of weights and gets the vertex ID, initializes a vertex ID and weight, and then sorts them to keep the 4 largest values, and hence this innermost loop is performing 4 iterations only, and the final values are stored inside the bone weights and the bone IDs. The header file also allows you to perform quaternion interpolation. So if it is a keyframe, it is taken directly. Otherwise, a weight is calculated based upon the current time minus the reference time and the total gap between them, and that is used to multiply the rotation value accordingly, the first one and the second one, to get the new interpolated value at the current time. And once the interpolation has been performed, the quaternion is converted back to a rotation matrix, and the position, the translation is also updated. Recall that every transformation to the bones and hence the mesh is applied from the rest pose. So starting from the rest pose, the transformation is applied. So for every bone in the mesh, we find out the node which is associated with this bone, and hence the inverse bone matrix that is associated with this node. Inverse bone matrix was explained in slide 16. It is the matrix that would take that bone back to the rest pose. And we use this rest pose matrix and multiply it with the current transformation matrix. And we do that recursively following the tree structure. So first we apply it to the root node, and then to its parent, to the leaf node, and then to its parent, and then to the parent of the parent until it reaches the root node. So this is the recursive algorithm that applies the inverse bone transformation matrix so that the current transformation is measured from the rest pose. This is the final bone transforms for the A bone. So in Blender, the animated character and its movement can be exported to several formats such as DirectX. You can also save them in the Blender native format, which is .blend, or the DirectX format which is .x. In your project part 2, you have exported them in the .x format, which can be read using the SIMP library. The DirectX file generated by Blender contains the hierarchical skeletal model and animation of the character. The data structure loaded onto OpenGL looks like this. For example, the .x file for the monkey head. So you'll have the armatures, so the frame armature, the frame armature of the torso, frame armature of the head, and their transformation matrices. So these transformation matrices will take them to their relative positions in the hierarchy. So it will take them, for example, their rest pose positions. The file also contains the vertices, and starting with the total number of vertices, then it lists them down as a set of 3 values that are the XYZ coordinates of the vertices, and then list the number of polygons. Polygons can be listed as 3 values which are indices into the vertices that form a triangle, or there could be 4 values, which simply means that the first 3 values forms one triangle and the last 3 values form another triangle. And then we have mesh normals. So there is one normal vector for every vertex, and if there is texture mapping, we'll have texture coordinates over here as well. And then we'll finally have the skin weights as to which armature affects which vertex by how much value. The last part of the DirectX file describes the animation. In this example, there are 81 frames starting from frame 0 to frame 80, and then the rotations are given in the form of quaternions, unit quaternions. So there are 4 values, and following this the scale is given, and the translation would have been given separately because quaternions can only describe rotations and not translations or scaling.